So in last lecture, we have seen the definition, classification of heat exchangers. We have seen the definition, classification and applications of heat exchangers. Now in this session, we'll see very important topic, which is analysis of heat exchangers. How heat exchangers are analyzed, how the dimensions of a heat exchanger are finalized. Now see, as far as analysis of heat exchangers is considered, the analysis is very simple. There are two types of analysis. Rather than types, I will say there are two methods. One is log mean temperature difference method, which is also called as LMTD method, and second method is effectiveness NTU method. Okay, before starting those types, in this today's session we'll see only LMTD method, that is log mean temperature difference method, right? Now for both methods, the analysis procedure is same. So initially we'll discuss what are the steps. Now see, first step is this. The first step is to apply first law of thermodynamics. What is first law of thermodynamics? First law of thermodynamics is nothing but law of conservation of energy. Energy can neither be created nor be destroyed. So if we think about a heat exchanger and if there are no losses, we can say that whatever is the heat given by hot fluid, that will be equal to heat accepted by cold fluid. What can we say? We can say that heat rejected by hot fluid is equal to heat accepted or heat absorbed by cold fluid. Now see, what is the heat given by hot fluid? Heat given by hot fluid is mHCpH into bracket Thi minus Tho. What is mH? mH is the mass flow rate of hot fluid. What is Cph? Cph is the specific heat of hot fluid. What are Thi and Tho? Thi and Tho is nothing but inlet and outlet temperature of hot fluid. So we can say that heat given by hot fluid is equal to mCp delta T. Now as it is hot fluid, we are using abbreviation H. So heat given by hot fluid will be equal to mH Cph into bracket Thi minus Tho. What will be heat accepted by cold fluid or heat absorbed by cold fluid? On the similar line, it will be mc Cpc into bracket Tco minus Tci. What is mc? mc is the mass flow rate of cold fluid. What is Cpc? Cpc is the specific heat of cold fluid. What is Tco? Tco is the outlet temperature of cold fluid. And what is Tci? Tci is the inlet temperature of cold fluid. Now see, if you look at the left hand side of this equation, here we are in the bracket, we have written Thi minus Tho, that is inlet minus outlet for hot fluid. And for cold fluid, we have written outlet minus inlet. Now why this difference is there? This difference is there because see, it will be higher temperature minus lower temperature. We are interested in the magnitude. We are not interested in the direction. We know the direction, that heat is flowing from hot fluid to cold fluid. So higher minus lower. In case of hot fluid, which temperature will be higher? Let's take example. You are cooling a fluid, right? That hot fluid is at 100 degrees Celsius. If it enters at 100, obviously it will leave at a temperature lower than 100. So inlet will be higher. So it will be Thi minus Tho as far as hot fluid is concerned. Now, if we talk about cold fluid, which temperature will be higher, inlet or outlet? It is obvious that as cold fluid is accepting the heat, its temperature will increase. So Tco will be more than Tci. So for cold temperature, in bracket we use Tco minus Tci. So very simple energy balance equation is there. That is heat given by hot fluid is equal to heat taken by cold fluid. So what the first equation is this? There are only 4 steps. I repeat, there are only 4 steps. The 2 steps I have written it on first slide. The first step is just now what we are discussing. The first step is to apply energy balance equation. What is that energy balance equation? It is mHCpH into bracket Thi minus Tho is equal to mCCpC into bracket Tco minus Tci. I believe that it is clear to you. Now what is the second step? The second step is to find the heat transfer rate. Now heat transfer rate you may consider QH or you may consider QC because both are same. In first step itself we have written QH is equal to QC. Now what is QH? Heat transfer rate of hot fluid, it is mh cph into bracket thi minus tho. Also, you can work out QC because both are same. How will you work out QC? It is MC CPC into bracket TCO minus TCI. So second step is to work out the heat transfer rate. I believe that both steps are clear to you. Very simple steps. In first step, see, out of four temperatures, THI, THO, TCI, TCO, only three temperatures are known to us. So we have to work out the fourth one using step number one, using energy balance. In second step, we have to work out how much should be the heat transfer rate. Being a heat exchanger, right? We have to consider the heat or find out the heat transfer rate. Okay. As I have told you, there are two methods, LMTD method and second is effectiveness NTU method. See, you can do like, you can work out or solve a question or numerical using LMTD method and you can cross check your answer using effectiveness NTU method. By both methods, you must get same answer. Now, in any design of heat exchanger, first it is required to find the area of the heat exchanger. What we are interested in, basically we are interested in how much area will be required for that heat exchange, for the desired heat exchange, right? Then from that area we can find out length of the heat exchanger, diameter of the tubes or the number of tubes required. So basically we are interested in the value of area, right? Okay. Now, if A is the area of heat exchanger, it will be equal to, if it is a single tube, then it will be pi dl. If n number of tubes are there, then area will be pi dl into n. Now, if number of passes are there, in last lecture, we have seen the concept of number of passes. 1 pass, 2 pass, 4 pass, right? If P is the number of tube passes, if N is the number of tubes, the total area of heat exchanger is given by the formula pi dl into N into P, where D is the diameter of tube, L is the length of tube, N is the number of tubes, and P is the number of passes. Okay, now we'll start with the first method, which is LMTD method. Now see, first thing is that we have to note down the given data. Now, while noting down the given data, what things we have to note down? We have to note down the mass flow rates. That is, we have to note down the mass flow rate of hot fluid and cold fluid. That is MH and MC. Now see, it should be m dot h, right? Because it is mass flow rate. What will be unit of mass flow rate? It will be kg per second. If it is given in kg per minute, you can divide it by 60 so that you can get your mass flow rate in kg per second. If it is given in kg per hour, then we can divide it by 3600 so that we can get the mass flow rate in kg per second. Okay, so the first step is to write down given data. In given data, you will write down the given data in a tabular format. I will show you that table. But what things we have to write down? First of all, we have to write down the mass flow rates of hot fluid and cold fluid. Then we have to write down specific heat capacities of both fluids. That is nothing but CPH and CPC. What is CPH? Specific heat of hot fluid. What is CPC? Specific heat of cold fluid. What is the unit of specific heat? The unit of specific heat is joules per kg Kelvin. I repeat, the unit of specific heat is joules per kg Kelvin. Then we have to, the overall heat transfer coefficient will be given. Overall heat transfer coefficient is nothing but U. Now see, out of the four temperatures, three temperatures will be known and we have to work out the fourth one. Generally inlet temperatures are known. So THI and TCI are known. And generally the outlet temperature of hot fluid is also given. So THO is also given. So we can work out TCO. So what is the first step? The first step is to write down the given data in a tabular format. Now see, when you will note down this table, you need not note down column number 3, which is units. It is just for your sake of understanding. You can just prepare only two columns. One is for hot fluid and second is for cold fluid. What will be first row? It will be mass flow rates. That is MH and MC. They should be in kg per second. Then what is the second row? Second row is specific heats, CPH and CPC. It should be in joules per kg Kelvin. Then you can note down the temperatures, THI, THO and TCI, TCO. Generally they are in degree Celsius, but even if they are in degree Kelvin or Fahrenheit, it will not hamper, right? See, okay, I believe that it is clear to you. Okay, so MH, MC, CPH, CPC, THI, THO, TCI, TCO. Next, At the end of the table, you have to write down the value of U. What is U? U is the overall heat transfer coefficient in watts per meter square Kelvin. So all these things you will note down. There may be a thing that out of 4 temperatures, only 3 temperatures are known to you. Let's say THI, TCI are known and THO is also known. So here in TCO, you can put down a question mark that TCO is not known to us. Then is the first step clear to you? I believe that the first step is clear to you. In first step, we have to write down the given data in a tabular format, right? Mass flow rates, specific heats and temperatures. At the end of table, we have to write down the value of overall heat transfer coefficient. Now, what was the first step? The first step is to apply energy balance equation. What is that energy balance equation? Yes, just now we have discussed that the energy balance equation is heat given by hot fluid is equal to heat absorbed by cold fluid. So it is mH Cph into bracket Thi minus Tho is equal to mc Cpc into bracket Tco minus Tci. Now if Tco is not known to us, but all these remaining things are known to us. We know mH, we know mc, we know Cph, we know Cpc, we know these 3 temperatures. So we can find out the 4th temperature. I believe that the first step is clear to you. Using first step, we will work out the unknown temperature. Out of 4 temperatures, if 3 temperatures are known, we can work out the 4th temperature using step number 1. So the step number 1 is to find out the unknown temperature from energy balance equation, which is nothing but QH is equal to QC. Now, what is the second step? Second step is to calculate heat transfer rate between hot and cold fluids. Either you can find QH or QC. Both values will be same. Okay, let's say I calculate QH. So how will I calculate QH? Simply either you calculate left hand side of equation 1 or calculate right hand side of equation 1. So if I calculate left hand side, it will be mH into Cph into bracket Thi minus Tho. If I do this simple calculation, what I can work out? I can work out the value of heat transfer rate. So the second step is to find out the heat transfer rate. So I repeat, the first step is to apply energy balance equation and calculate the 4th unknown temperature. And second step is to find out the heat transfer rate. Now, the third step is to draw temperature profile. Now, before drawing temperature profile, we must know what type of heat exchanger it is. If it is parallel flow, the temperature profile will be different. If it is counter flow, the temperature profile will be different. In last section, we have discussed this. This is the temperature profile for parallel flow heat exchanger. Both fluids, they are flowing in same direction. See, this is THI. What is the meaning of THI? Inlet temperature of hot fluid. What is THO? Outlet temperature of hot fluid. What is TCI? Inlet temperature of cold fluid. What is TCO? Outlet temperature of cold fluid. Now, if I work out temperature difference on the left side, before that, tell me, is this temperature profile clear to you? THI, THO are inlet and outlet temperatures of hot fluid. It is obvious that temperature will drop. TCI, TCO are inlet and outlet temperatures of cold fluid. It is obvious that temperature will rise. Now, what is theta 1? Theta 1 is the temperature difference on left hand side of the heat exchanger. Now, what will be temperature difference on this side? It will be THI minus TCI. Okay. What will be theta 2? Temperature difference on other side of the heat exchanger? It will be THO minus TCO. So last step is this. In last step, we have to work out theta 1 and theta 2. Is it clear to you? What is theta 1? For parallel flow heat exchanger, it will be THI minus TCI, and theta 2 will be equal to THO minus TCO. Once the values of theta 1 and theta 2 are known to you, the next step is to calculate LMTD. But before that, we'll see temperature profile of counter flow heat exchanger. Now see, this is the temperature profile for counter flow heat exchanger. Counter means both fluids are flowing in counter directions, means opposite directions. This is THI, THO, this one is TCI and TCO. See, hot fluid is flowing from left hand side to right hand side and cold fluid is flowing in the opposite direction. Now in this case, what will be temperature difference on this side? What will be theta 1? For counter flow heat exchanger, theta 1 will be equal to THI minus TCO. And what will be theta 2? Theta 2 will be equal to THO minus TCI. So we can find theta 1 and theta 2. So this was the third step. The third step is to draw temperature profiles and calculate theta 1 and theta 2. Now, the fourth step is to find LMTD. LMTD means log mean temperature difference. Now see, there is derivation for this, but in today's session, we will not see the derivation. Maybe in next session, if the time permits, we'll see this derivation. At this moment, you just remember this formula. What the formula is, how to calculate LMTD or theta m. The formula is theta m is equal to theta 1 minus theta 2 upon ln of theta 1 by theta 2. What is ln? Ln is nothing but natural log, log to the base e. So how can we calculate theta m? Simply by knowing the values of theta 1 and theta 2, we can calculate theta m. What is the formula for theta m? The formula for theta m is theta 1 minus theta 2 divided by ln of theta 1 upon theta 2. I believe it is clear to you. Now see, if I talk about parallel flow heat exchanger, theta 1 will be equal to Thi minus Tci. If I talk about counter flow heat exchanger, theta 1 will be equal to Thi minus Tco. If I talk about parallel flow heat exchanger, theta 2 will be equal to Tho minus Tco. If I talk about counter flow heat exchanger, theta 2 will be equal to Tho minus Tci. So theta 1 and theta 2, these values will change for parallel flow and counter flow. Okay. I think it is clear to you. How to calculate theta m? To calculate theta m, the formula is theta 1 minus theta 2 upon ln of theta 1 by theta 2. Now see, we have seen for parallel flow and counter flow, how to calculate theta 1 and theta 2. Now, if the heat exchanger is cross flow type of heat exchanger or any type of heat exchanger, let's say shell and tube heat exchanger, then how to find theta m for that heat exchanger? There is an equation that theta m, which is nothing but log mean temperature difference, theta m is nothing but LMTD, that is log mean temperature difference, for any type of heat exchanger is equal to correction factor F into theta m for counter flow heat exchanger. I repeat, theta m for any type of heat exchanger is equal to theta m for counter flow type of heat exchanger into correction factor. Now see, this correction factor is calculated from the charts, but in as far as your exam is concerned, the value of this correction factor will be given to you. Okay, so I believe that this step is clear to you. So what was the first step? The first step was to apply energy balance equation and work out the fourth unknown temperature. What was the second step? The second step was to work out the heat transfer rate. What was the third step? Third step was to draw temperature profiles and work out the values of theta 1 and theta 2. And what was the last step? The last step was to work out theta m. If parallel flow or counter flow is there, then we can work out theta m directly, right? If any other type of heat exchanger is there, what formula we have to use? We have to use the formula that theta m for any type of heat exchanger is equal to F into theta m for counter flow heat exchanger, where F is the correction factor. And the last step is we have to use the equation Q is equal to UA theta m. We have to apply the equation Q is equal to UA theta m. Now what is Q? In second step, we have calculated Q. Q is the heat transfer rate. What is U? U is the overall heat transfer coefficient. What is A? A is the area required for heat exchanger. And what is theta m? Theta m is nothing but log mean temperature difference. Now see, in second step, we have calculated Q. U is given to us. In the numerical itself, the value of overall heat transfer coefficient will be given to us. Theta m we have calculated in fourth step. So only what is unknown? Unknown is A. And this was the objective. Designing a heat exchanger means we have to design, we have to find how much area will be required for the heat exchange to occur. Okay. Now once we know that area, right? Once we know that area, we can work out number of tubes or number of passes. Now see, area of the heat exchanger is equal to pi dl into n into p. Simple formula is there. What is pi dl? Area of single tube. Let's say tube in tube kind of heat exchanger is there. So only the formula will be pi dl, right? If shell and tube heat exchanger is there, what will be formula? Area will be equal to pi dl into n into p. What is this n? N is the number of tubes. We have discussed in last lecture. In shell and tube heat exchanger, number of tubes are used. So n is the number of tubes. What is p? P is the number of passes. I believe that it is clear to you. So from this, Either we can work out length of the heat exchanger required, or we can work out how many tubes are required, or we can work out how many passes are required. Okay, so I will just repeat the steps and we will work out one numerical. What are the steps? The first step is to apply energy balance equation and to find out the fourth unknown, temperature. What is the second step? The second step is to calculate heat transfer rate. Either you can find QH or QC. What is the third step? The third step is to draw temperature profiles, and from temperature profiles we can work out theta 1 and theta 2. What is the last step? The last step is to find theta m. Theta m is nothing but log mean temperature difference. Log mean temperature difference is defined as the temperature difference which can be assumed to be constant throughout the length of the heat exchanger, which will have same heat transfer rate as that in the actual case. So I will give you one example. In case of IC engines, we consider mean effective pressure. Pressure at every point it is different. 1 to 2, 2 to 3, 3 to 4, and 4 to 1. The pressure is different. But we assume that throughout the cycle, the pressure is constant, which is equal to mean effective pressure, using which we'll obtain the same work. So here the concept is similar. If you try to carry out design of heat exchanger, let's take this example. At the left end, the temperature difference is THI minus TCI. Somewhere over here, the temperature is this much. If I again proceed along the length, the temperature difference is changing. So because of this, the design of heat exchanger, the analysis of heat exchanger becomes complicated, because at every section, the temperature difference is different. So what we can do, we can assume a hypothetical temperature difference which is constant throughout the length of heat exchanger, which will give us same heat transfer as that in the actual case. And that hypothetical, that imaginary temperature difference is called as log mean temperature difference. In tomorrow's session, when we'll see the derivation for LMTD, the concept will be more clear to you. But what is the concept? At this moment, you should understand the concept. What is the concept? Log mean temperature difference is the temperature difference which is assumed to be constant throughout the length of heat exchanger, which will give us same heat transfer as that in the actual case. So we can imagine that throughout the length of heat exchanger, the temperature difference is constant, which is nothing but theta m. Okay, so the last step is to calculate theta m, right? And what is the formula for theta m for cross flow heat exchanger or theta m for shell and tube heat exchanger? The formula is correction factor into theta m for counter flow heat exchanger. Okay. And what is the last step? We can calculate the area, right? How can we calculate the area? Simply we can apply the equation Q is equal to UA theta m, where Q is the heat transfer rate, U is the overall heat transfer coefficient, theta m is log mean temperature difference, and A is the area required for heat transfer. So we can work out A. Once A is known, we can work out length or number of passes or number of tubes. Okay. Now see, we'll just see this numerical. What is given in this numerical? I will just read the numerical for you. Determine the heat transfer surface area and length required for a heat exchanger constructed from a 25.4 millimeter diameter tube. So diameter of the tube is given as D is 25.4 into 10 raised to minus 3 meters. Always we take dimensions in meters. Now, to cool 6.93 kg per minute of ethyl alcohol solution. Now, ethyl alcohol is to be cooled. So, ethyl alcohol is nothing but the hot fluid, right? 6.93 kg per minute. So, what is given? Mass flow rate of hot fluid. It is given as 6.93 kg per minute. See, whenever we write given data, we'll write down given data in a tabular format as far as numericals of heat exchangers are considered, right? So mh is given. It is given how much? 6.93. But can I take the value as it is? No, because the unit is kg per minute. What I will do? I will divide this 6.93 by 60. And I will write the unit in kg per second. Is it clear to you? So value of mh is given. Then Cp is given. Now this is hot fluid. So this is nothing but Cph. How much is given? Cp is 3810 joules per kg Kelvin. So the value of Cph is given. Now, it is to be cooled from 65.6 degrees Celsius to 39.4 degrees Celsius. So what is given? This is inlet temperature of hot fluid and this is outlet temperature of hot fluid. The ethyl alcohol solution is to be cooled from 65.6 degrees Celsius to 39.4 degrees Celsius. So this is nothing but THI and this is nothing but THO. Now, what is given in next para? Is the first para clear to you? What is given? D is given, MH dot is given, CPH is given, and THI and THO is given. Now, what is given in the second para? Water in bracket Cp, the value of Cp of water is given at 10 degrees Celsius is available as a coolant. So water is coolant. So water is cold fluid. It will absorb heat, right? So this is nothing but CPC, Cp of the cold fluid, specific heat of the cold fluid. CPC is given as 4178 joules per kg Kelvin. Now 10 degrees Celsius, that is TCI. Water enters at 10 degrees Celsius means inlet temperature of cold fluid is 10 degrees Celsius. So what is given? TCI. So it is flowing at a flow rate of 6.3 kg per minute. This is mass flow rate of cold fluid. So it is 6.3 kg per minute. So this is MC dot 6.3 divided by 60 kg per second. Okay. Below the table, at the end of table, what we write? Overall heat transfer coefficient. What is the symbol for overall heat transfer coefficient? It is U. So U is given as 568 watts per meter square Kelvin. Now consider the following arrangements. This is a lengthy numerical but in this numerical, all types of heat exchangers will be clear to you. So what are the different arrangements? The first arrangement is parallel flow tube-in-tube type of heat exchanger. The second is counter flow tube-in-tube type of heat exchanger. Third is cross flow heat exchanger with 10 tubes and correction factor 0.88. And last one is shell and tube heat exchanger with 6 tubes, correction factor 0.97 and single tube pass. So we'll discuss one by one. Initially, what we'll do? Initially, we'll prepare the table. MH dot is given. It is given in kg per minute. We can convert it in kg per second. MC dot is given. CPH is given. THI, THO are given. CPC is given. TCI and TCO are given. Now see, Cp is specific heat. Its unit is joules per kg Kelvin. If it is given in kilojoules per kg Kelvin, we can convert it into joules per kg Kelvin. In this numerical, it is given in joules per kg Kelvin. CPH is given as 3810 and CPC is given as 4178 joules per kg Kelvin. So we can write down these values. We can write down the values of THI and THO. We can write down the value of TCI. TCI is nothing but 10 degrees Celsius. And what will be first step? The first step is to work out fourth unknown temperature. In this case, what is the unknown temperature? TCO. How can we work out TCO? Simply apply the energy balance equation. MH dot CPH into bracket THI minus THO is equal to MC dot CPC into bracket TCO minus TCI. If you apply that simple equation, you will get the value of TCO. Is it clear to you? Simply you have to apply energy balance equation. MH CPH into bracket THI minus THO is equal to MC CPC into bracket TCO minus TCI. Using this, you can work out the unknown temperature. What will be the second step? In second step, what we have to find? In second step, we have to find Q. How can we find Q? Simply you can find QH or QC. What is the equation to find QH? MH CPH into bracket THI minus THO. Just calculate that value. That value is nothing but Q. You can cross check your answer. Just apply the equation QC is equal to MC CPC into bracket TCO minus TCI. You must get the same answer. Now that answer is nothing but Q. So I believe first two steps are clear to you. First is energy balance equation. Second is to calculate heat flow rate or heat transfer rate. Now what is the third step? The third step is to apply temperature profile. Now we'll see the heat exchanger. 4 different heat exchangers are there. Generally in numericals only one heat exchanger will be there, right? But in this numerical we will consider 4 different heat exchangers. So just consider first heat exchanger, which is nothing but parallel flow heat exchanger. So if it is a parallel flow heat exchanger, the temperature profile will be like this: THI, TCI, THO, TCO. How can we calculate theta 1? Simply theta 1 is nothing but THI minus TCI. How can we calculate theta 2? THO minus TCO. So we know the values of THI, TCI, THO, TCO for this case. So we can calculate theta 1 and theta 2. Once we know the value of theta 1 and theta 2, how can we calculate LMTD? Simply apply the equation LMTD theta m is equal to theta 1 minus theta 2 divided by ln of theta 1 by theta 2. So if we apply this equation, you will get theta m. See, for this present numerical, you will get values of theta 1 and theta 2 as this. You will get theta 1 as 55.6 degrees Celsius, theta 2 as 3.12 and theta m as 18.22. Now what is the last step? In last step, we apply equation Q is equal to UA theta M. You know the value of Q. See, this is the value of Q, 11592 watt. You know the value of U. Q is equal to UA theta M. You know the value of theta M. So you can calculate A. Once A is known to you, this is tube in tube kind of heat exchanger. So only one tube is there. So A is equal to pi dl. The value of diameter is known to us. So we can work out length of the heat exchanger. Is it clear to you? I believe that this is clear to you. So this is one type of heat exchanger, which is parallel flow heat exchanger. Then we'll move on to second type. What is second type? Counter flow heat exchanger. How is the temperature profile for counter flow heat exchanger? For counter flow heat exchanger, both fluids are flowing in opposite direction. So we get this kind of temperature profile. Now, for this case, what is theta 1? It is temperature difference on left side. It will be Thi minus Tco. What will be temperature difference on right hand side? It will be Tho minus Tci. So for this case, we can calculate theta 1 and theta 2, and once theta 1 and theta 2. See, for this case, for the present numerical, for the values given in this numerical, you will get these as the values of theta 1 and theta 2. You will get theta 1 as 29.32, theta 2 as 29.4. If you apply the formula of LMTD, which is nothing but theta m is equal to theta 1 minus theta 2 upon ln of theta 1 by theta 2, you will get value of theta m as 29.36. What will be last step? You will use the equation Q is equal to UA theta M. You know the value of Q, you know the value of U, you know the value of theta M. For this case, theta M is 29.36. So you can work out the value of A. For this case, for counter flow, you will get value of A as 0.6913. And once A is known, how will you find length of heat exchanger? Simply we will apply equation A is equal to pi dl. See, basically the equation is A is equal to pi dl into N into P. But here number of tubes is 1 and number of passes is also 1. So you will use equation A is equal to pi dl and you will calculate length of the heat exchanger. Now see, we'll consider last part of the question. Let's say cross flow type of heat exchanger is there. What is the formula to calculate theta m for cross flow type of heat exchanger? We have seen theta m for any type of heat exchanger is equal to correction factor into theta m for counter flow heat exchanger. We have calculated theta m for the counter flow. How we calculate theta m for counter flow? It is theta 1 minus theta 2 upon ln of theta 1 by theta 2. For counter flow, what is theta 1? See, this is the temperature profile for counter flow. What is theta 1? Thi minus Tco. What is theta 2? Tho minus Tci. So already we have done this. So just remember that if any type of heat exchanger comes, you have to consider the temperature profile for counter flow. You have to calculate theta m for counter flow, and you simply have to apply that, multiply theta m for counter flow with correction factor, so that you will get theta m, that is LMTD for your heat exchanger. Right now, theta m for counter flow was, just now we have worked out, it was 29.36. So if we apply that by correction factor, in the numerical it was given that for cross flow heat exchanger the correction factor is 0.88. So if you multiply this by this, you will get the answer as 25.836. So theta m for cross flow in present case is this. Right? Once theta m is known, you can work out area. How will you work out area? Q is equal to UA theta m. The value of Q is known to you, U is known to you, theta m is this much, you can calculate A. Now, how will you find length of the heat exchanger? You will use the formula A is equal to pi dl into N into P. Now see, as far as cross flow heat exchanger is considered, what is given in this? 10 tubes are there, right? And correction factor is 0.88. So F was given as 0.88 and 10 tubes, number of tubes is given as 10. So what formula you will use for A? A is equal to pi dl into N into P. Number of passes is not given, so we'll assume that single pass is there. And number of tubes are given as 10. So A is equal to pi dl into 10 into 1. Right? So D is known, number of tubes is known, number of passes are known. So you can work out length of the heat exchanger. I believe that it is clear to you. Even if it is not clear to you, just focus on this. In this also, in shell and tube and cross flow, the procedure is one and the same. Let's take last case, shell and tube heat exchanger. What is given in the numerical? Shell and tube heat exchanger with 6 tubes. 6 tubes means N is equal to 6. Number of tubes is 6. Correction factor is 0.97. F is equal to 0.97 and single tube pass. So number of passes P is equal to 1. I repeat, what is given? N is equal to 6. Number of tubes are 6. F is equal to 0.97 and single tube pass means P is equal to 1. Okay. Now, how we calculate theta m for shell and tube heat exchanger? The formula is theta m for shell and tube heat exchanger is equal to correction factor into theta m for counterflow heat exchanger. So we'll consider calculated theta m for counterflow, which worked out to be 29.36. If we multiply that by correction factor, we'll get theta m for shell and tube heat exchanger. So in this case, you will get theta m as 28.47. What will be next step? The next step is to calculate area, right? How we find area? To find area, we use equation Q is equal to UA theta m, right? Q in the second step we have worked out. U, it is given in the numerical. A is what we are supposed to find and theta m is what we calculate in the fourth step, right? Okay, after calculating A, we have to find length of tube, right? Okay, how we calculate length of tube from area? We use the formula A is equal to pi dl into N into P. I repeat, A is equal to pi dl into N into P, where N is the number of tubes and P is the number of passes. In this case, number of tubes was 6, number of passes was 1. So you can work out length of the heat exchanger, which will come out to be 1.488. Is it clear to you? So in log mean temperature difference method, only 4 steps are there. I will just repeat those 4 steps and then we'll stop. In the analysis of heat exchangers, firstly, we apply energy balance equation. That is, heat given by hot fluid is equal to heat absorbed by cold fluid. That is, QH is equal to QC. See, in industrial design, this will not be there. Some losses are there. The equation will be QH is equal to QC plus losses. Those losses we have to consider and we have to minimize those losses, right? Being a heat exchanger, obviously we will expect that all heat given by hot fluid should be accepted by cold fluid, but it will not be true. 100% of the heat given by hot fluid will not be accepted by the cold fluid. Some losses are bound to exist, right? But as far as theoretically we consider that all heat given by hot fluid is absorbed by cold fluid. So we apply this energy balance equation, right? What is this energy balance equation? MCP delta T of hot fluid is equal to MCP delta T of cold fluid. What is M? Mass flow rate in kg per second. What is CP? Specific heat in joules per kg Kelvin. And delta T, higher minus lower. THI minus THO and TCO minus TCI. Already I have told you why this is THI minus THO and why this is TCO minus TCI. In case of hot, why it is inlet minus outlet, and in case of cold, why it is outlet minus inlet. Higher minus lower. In case of hot, which will be higher? Inlet will be higher than outlet. In case of cold, outlet will be higher than inlet. Okay. MCP delta T of hot is equal to MCP delta T of cold. Simply apply this equation and work out the fourth unknown temperature. This is your step number 1. What is step number 2? Step number 2 is to find the heat transfer rate required. Either you can use Q is equal to MHCPH MCP delta T of hot, or you can use Q is equal to MCP delta T of cold. Using both equations, you can find the heat transfer rate required. This is the second step. The third step is to draw temperature profile. This is the temperature profile for parallel flow heat exchanger. Now see, temperature difference on left side is parallel flow means both directions are same. Counter means one direction will be opposite to the other. Okay, we are discussing about parallel flow. What will be theta 1? THI minus TCI. Temperature difference on left side will be THI minus TCI. What will be theta 2? It will be THO minus TCO, right? If it is counter flow, what will be theta 1? THI minus TCO. What will be theta 2? THO minus TCI. Okay. Then how we calculate LMTD? Simply we apply equation theta m is equal to theta 1 minus theta 2 upon ln of theta 1 by theta 2. Now this is the formula to calculate LMTD for parallel flow or counter flow. Now how will we calculate theta m for any other kind of heat exchanger? The formula is theta m for any other kind of heat exchanger is equal to correction factor into theta m for counter flow. Why this formula is there? Because counter flow heat exchangers are the most effective heat exchangers. In next lecture we'll see why. For the same arrangement, even if we only change the direction, right, counter flow heat exchangers are more effective. Okay, using this expression we compare any other types of heat exchangers with counter flow. So theta m for any type of heat exchanger is equal to correction factor into theta m for counter flow. And lastly, we use the equation Q is equal to UA theta m. What is our area of interest? Our area of interest is to find A. How much area is required for heat exchange to occur? Q is what? Q is the heat transfer rate of hot fluid or cold fluid. It is in watts. U is overall heat transfer coefficient. Theta m is log mean temperature difference. So if these three things are known to me, Q, U and theta m, if these three things are known to me, I can calculate A. A is nothing but area required. Now, once I know the area, I can work out length of tubes. If n number of tubes are there, P is the number of passes. I will use A is equal to pi d L into N into P, where D is the diameter of tube, L is the length of tube, N is the number of tubes, and P is the number of passes. I believe that it is clear to you. Okay, we'll stop here.